So as it turns out, there's more than one way to draw formaldehyde. So let's go back to what we did initially with formaldehyde, which was to draw its structure like so. So that was what we initially did. Then in the previous video, we recognized that this is an sp2 carbon. As such, the groups around it are arranged in a trigonal planar geometry. And so we redrew the structure to try to reflect that trigonal planar geometry and the appropriate bond angles. Now the bond angles in a trigonal planar around a trigonal planar atom would be roughly 120 degrees. So we redraw the compound to try to approximate that. But that's not what I mean by saying that there's more than one way to represent the structure. So over here on the right, I'm going to draw a different way of drawing formaldehyde. Or I'm going to show a different way of drawing formaldehyde, I should say. So instead of having two lone pairs around the oxygen, I'm going to put three, which means I'm going to take a pair of electrons out of the double bond and put it on the oxygen. Now these structures that we've just drawn have a relationship. These are called resonance structures. Or resonance contributors. The structure on the right has some things missing. And so to assess that, we need to learn how to assess formal charge. So I'm going to give you a formula. You've probably seen a formula for formal charge before. It might be in a slightly different format than the one that I'm going to give you, but it's going to get you to the same place. So whatever formal charge formula you learned, you can go ahead and use that because it's going to be fine. The formal charge on a particular atom we calculate by taking the valence number of the atom. And from that, we're going to subtract all the non-bonding electrons on the atom. So any electrons that are on the atom that are not involved in bonds, plus the number of bonds to the atom. That gives us the formal charge. So let's do this for the structure on the left. So for carbon, the valence number of carbon is 4. In terms of structure on the left, I'm referring to this one right here. We're all on the same page. So the valence number of carbon is 4, and we're going to subtract from that the number of non-bonding electrons, which in that structure on that carbon, there are no non-bonding electrons, so that number is 0, and the number of bonds. And that carbon has 4 bonds. So its formal charge is 0. For the oxygen, the valence number is 6, and from that, we subtract non-bonding electrons. Well, we have 2 lone pairs, so that's 4 non-bonding electrons, and that oxygen is involved in 2 bonds. So 6 minus 6 also equals 0. For the structure on the right, to repeat the calculation for carbon, the valence number is still 4. We subtract off any non-bonding electrons. There are no such electrons on that carbon in that structure, so that's 0. And we also subtract off the number of bonds. There are 3 bonds to that carbon. That gives us a formal charge of +1. And for the oxygen, valence number is still 6. We subtract off the number of non-bonding electrons. We have 3 lone pairs, so there's 6 of them. And the number of bonds, there's 1 bond. So the formal charge on the oxygen is -1. So now we can put those symbols on the structure. So we'll put a plus next to the carbon and a minus next to the oxygen. So now the structures are complete. So these two structures of formaldehyde, when we take them together, when we take them in concert, make up what's called a resonance hybrid. The resonance hybrid is the overall description of the molecule. So the resonance hybrid is the overall description of the molecule or the ion, because we could do this for ions as well. So let's add that in, molecule or ion. And so each of the structures, the reason we call them contributors is because each one of them is contributing something to the resonance hybrid. It's contributing something to our overall understanding of the structure of this molecule. So what does this mean? What is this all suggesting? First of all, the fact that formaldehyde and other molecules have additional Lewis structures means that there can be more than one reasonable Lewis structure for certain molecules. So first, there can be more than one. Reasonable Lewis structure. And we'll get into what we mean by reasonable. For certain molecules. So not all of them, but some of them. Now notice that we're saying for certain molecules, as opposed to certain molecular formulas. If you can draw different structures, different Lewis structures for the same molecular formula, remember those are constitutional isomers. But in this case, we're not arranging the atoms in a different order. The atoms are bonded in the same way in both of the structures. It's just that the electrons are distributed differently. Now, what does that mean? That the electrons are distributed differently? Well, in molecules that have resonance or that exhibit resonance, certain of the electrons within those molecules are delocalized. So in molecules with resonance, certain electrons are what we call delocalized. That's an important term. It's one that you're going to hear a whole bunch. Delocalized, when we refer to electrons using that term, means that those electrons are not confined to a particular atom or just one bond. So they're not confined to a particular atom or bond. Instead, they're spread out over multiple bonds and multiple atoms. Typically, when that happens, the delocalization of electrons lowers the energy of the structure that they're contained in. So it typically lowers the energy. We'll use capital E for energy, so we don't have to write out energy every time, of the structure they're in. Okay. So what we're going to do in this video is look at the overview of resonance. We're going to get the big picture of resonance, and then in the subsequent video or videos, what we're going to look at are what are the moves we can make? How do we actually, in practice, draw resonance given a set of structures or given a structure? So let's start by looking at something called curved arrow notation. Now, curved arrow notation is everywhere in organic chemistry. So it's important to learn this and to start getting comfortable with it early on. So curved arrows show the movement of electrons. Now that can either be a real movement, for example, in a reaction, a chemical reaction between two partners. Let's say one of them has some electrons that it's able to share with the other one so that it can form a bond to it. That would be a real movement of electrons. The electrons are moving from one chemical to the region between the two chemicals to link them together in a chemical bond. So that would be a real movement of electrons. Or an imaginary movement of electrons can also be depicted using this curved arrow notation. When we think about imaginary movement of electrons, that's when we're thinking about resonance. So I'll get into what I mean by imaginary in a little bit. But for now, let's just kind of get the hang of these arrows. The arrows that we draw are always going to start at electrons, and they're going to point to where those electrons end up in the next structure that we draw. So there's going to be two types. One of them is a typical arrow. It has two barbs at the end, and this is showing two electrons moving together as a pair. The other type of arrow that you could use has just one hook at the end, or one barb. That's called a fishhook arrow, and that's showing one electron moving by itself. So we're going to use the curved arrow notation in the context of resonance to show how two resonance contributors are related to one another. So I'm reproducing the drawings of formaldehyde from the previous page, incorporating all the non-zero formal charges that we calculated. So here we have the two structures. Okay, to get from the structure on the left to the structure on the right, mentally what we did, okay, so this is not happening in real life to this molecule, but mentally what we did was we took a pair of electrons out of the double bond and we put it onto the oxygen. So to show that process, that thought process, using curved arrow notation, you would start an arrow at the double bond between the carbon and the oxygen and point to the oxygen. So again, this is an imaginary movement. The curved arrows in resonance are imaginary movements of electrons. The electrons are not really moving. Instead, they're delocalizing, and this is our crude way of depicting that. So the electrons in this case, remember, delocalization means that the electrons are not confined to a particular bond or a particular atom. What we see in formaldehyde is that electrons are spread out between the double bond and the oxygen. So they're being shared by those 2 points in the molecule. So the electrons are not moving, but rather they are delocalized. Now, as long as we're on the topic of arrows, let's think about some other arrow notation. So this first example, here's an arrow that has barbs at both ends. So a single line with barbs at both ends. This is the resonance arrow. What this arrow is telling you is that A and B, whatever those chemical species are contributors to the same resonance hybrid. So that's the resonance arrow. The second is a pair of arrows that you've seen before. So one arrow pointing to the right, the other arrow pointing to the left. So you'll probably remember what that means is that A and B, whatever they are in equilibrium. So if two things are in equilibrium with each other, we say they are equilibrating. Or if a system of things, an assortment of chemicals, is in equilibrium, we would say that that system is equilibrating. Okay, so just based on those two things, what we just looked at, those two arrow types, so this guy here and this guy here, notice that we're using a completely different arrow in each case. What that should remind you, or hopefully will remind you going forward, is that resonance is not the same as equilibrium. Very important. In equilibrium, A is turning into B, and then B is turning back into A. And that process is just going on constantly. The rate at which A turns into B is the same as the rate at which B turns into A. Okay, so they're in equilibrium with each other, but they're interconverting. In resonance, the structures are not interconverting. So in resonance, structures are not interconverting the way they are in a chemical equilibrium. So what that means, if we go back, let's go back up to formaldehyde. Formaldehyde doesn't exist part of the time as a structure on the left and the other part of the time as a structure on the right. Rather, both of these are viable ways and reasonable ways of describing the structure of formaldehyde. It's just that one Lewis structure, in the cases of molecules with resonance, one Lewis structure doesn't really cover it. We need different structures to reflect different features of the molecule. Now this last arrow, going from A to B, just pointing in the forward direction towards the product, we can just call this a reaction arrow. And what this is telling us is that A reacts to produce B. Okay, so the resonance hybrid. So we started with Lewis structures a little while ago. We reviewed what it takes to draw a Lewis structure, how you put one together. Then we started looking at different ways of drawing organic molecules, and then we extended our discussion to different functional groups, which is going to hopefully make our drawing a little bit easier. If we know, for example, again, that we have to draw a ketone, we know what functional motif that's going to incorporate. So another thing that we're going to have to add in to the mix here is if we have a molecule, how do we know if we can draw resonance structures for that? Is resonance possible in a particular structure? So the way that we're going to do that is to look for certain structural features and patterns. So there are going to be certain markers that we're going to be able to identify that are going to tell us not only whether we can draw resonance, but what moves we can make. So let's say that we've drawn a set of resonance structures for a particular compound. So we have more than one. So that's the second idea. If there's more than one, how can we tell which one is the best? That would be the one that would contribute the most to the resonance hybrid. That if we had to pick one, what's the best possible depiction of this molecule? We would call that the major contributor. So we're going to look at ways to assess that on coming up. So we're going to end up using the same set of moves, the same set of patterns when we draw resonance. And fortunately, there's only a handful of these. So all we have to be able to do is recognize the pattern and then be able to know what we do with that pattern. So we can call these allowable moves. And we'll look at those in the next videos, as I mentioned. But as we're doing this, let's keep an eye on the big picture. First of all, let's say that we've drawn a set of resonance structures for a molecule. Remember that that molecule, or ion, is described by all the contributors to the hybrid. And again, because this bears repeating, the contributors are not interconverting. So a molecule or an ion doesn't exist part of the time as one of its resonance contributors, and the other part of the time as another one, and still another part of the time as a third one, and so on. They're not turning back and forth into each other. They're not interconverting. They all exist simultaneously. It's just that some of them are better descriptions of the molecule than others. Okay, so whatever the moves are that we make, and we're only going to make, again, the permitted moves or the allowable moves, if we consider all the contributors to the hybrid, there are going to be some things that are always the same. It doesn't matter what set of resonance structures we're looking at. First of all of the atoms among all of the structures are always in the same position. So all the atoms stay in the same position. So for example, if we took the two structures of formaldehyde that we drew previously, and let's say that we plotted them, and we placed them on a coordinate axis. So let's say we put the carbonyl carbon at the origin of the coordinate axis, so 0, 0. The coordinates for the oxygen and the other two hydrogens are going to be the same for one structure as they are in the other structure. So between the structures, the atoms are not moving around. They're always fixed in position. They have the same coordinates, if you will. What this means is that bond angles stay the same across the hybrid, meaning that the molecule doesn't have different bond angles. Okay, the bond angles are always going to be the same. Finally, all the contributors to a particular hybrid have to have the same net charge. So they have to have the same net charge. This makes sense because they all have the same number of valence electrons. We're not putting new electrons in or taking electrons out. We're just drawing them in different places within the structure. So as such, they all have to have the same net charge. Okay, let's take a look at that second bullet point up above, which says if there's more than one structure, how do we know which ones are better than others? So let's take a look at some ideas. Now, in this set of exercises or concepts that we're going to be talking about on this page, we're going to be drawing some resonance structures and drawing the curved arrows and so on. And these are going to reflect patterns that we're going to look into in detail in the next video. So for now, take these movements and what I'm drawing on faith. We're going to get into the weeds on this as we go forward. So let's start again with formaldehyde. Now that we've drawn formaldehyde about 300 times, let's draw it a few more times. So let's draw the two contributors to the formaldehyde resonance hybrid. Okay. They both don't contribute equally to the hybrid. One of them is a better picture of formaldehyde. We would call that the major contributor than the other one. We would call the other one the minor contributor. Now in this case, the structure on the left, as it turns out, is the major contributor, and the structure on the right is the minor contributor. So the major contributor is the better overall description of the molecule. So we'll say best in case we have a case where we have more than 2 contributors, which is frequently the case. So the major contributor is the best overall description of our molecule or ion. However, a minor contributor can still give us, and often does give us, important information. So let's take a look at that. Minor contributors impart important details. Okay, so let's think about this for formaldehyde. So once again, for the 3000th time, here's formaldehyde. And so what we recognize as a major contributor, what we recognize right away in formaldehyde, all covalent bonds. These are all covalent bonds within the structure. And in particular, the one between the carbon and the oxygen, we can put another designation on. We know that oxygen is more electronegative than carbon, which means that it likes to pull the electrons closer to itself than does carbon. So it's pulling the electrons in that bond toward itself. And we can depict that using that symbol that I just drew, which is called a dipole. The dipole points to the more electronegative element in the bond, and then on the less electronegative side, there's a little plus across the end of the arrow. Another way that organic chemists have of drawing that, I just can't get enough of drawing formaldehyde. I think you might have noticed at this point. Another way that organic chemists have of showing this, showing dipoles, is to assess partial charges. So for example, the oxygen is drawing electron density from the bond towards itself. So it has a little bit more electron density than the carbon. So we can say that even though it doesn't have a full negative charge, it has a partial negative charge, which we abbreviate as delta minus. Similarly, the carbon is having electron density pulled away from it. So that's leaving it with a slight partial positive charge. So delta plus and delta minus are the symbols we use for partial positive and negative charges. Now, if we apply these ideas, or this idea, the point here is that a minor contributor can impart important ideas or important details. So in the minor contributor, look at what we have. We have a full negative charge on oxygen and a full positive charge on the carbon. That's a reflection of that dipole. So this is one of the things that you might see in the minor contributor. Now in this case, it's fairly obvious because we can look at the major contributor like we just did and say, oh, there's a dipole, and so the carbon is going to be slightly positive and the oxygen is going to be slightly negative. And what that tells us might be something about how this compound could potentially react with something else. So for example, let's say that there's another chemical that approaches formaldehyde and it has a lot of electron density that it can share to make a bond with something else. It might be drawn to that partial positive charge on the carbonyl carbon. So this is one of the things that we can glean from a minor contributor. Okay, so if you have a set of resonance contributors that you need to assess, figure out which one is the most important, and so on, the very first thing, number one, that you're going to go to is to check the octet rule for all of the atoms in the compound. Losing track of the screen here. And the question you're going to ask is the octet rule satisfied for all the atoms that need octets? And just to remind you, this should be the very first thing that you assess. Okay, so some ideas about this. First of all, when you're drawing your structures, oxygen and nitrogen should always have octets. So they should always have 8 electrons around them. They should always have octets. But remember, period 2 elements cannot exceed the octet. So that includes carbon, nitrogen, oxygen, fluorine, boron also. So they cannot exceed, let's make it general, period 2 elements can't exceed the octet. So don't be drawing structures that have 10 or more electrons around any period 2 element, including, perhaps most importantly, carbon, because you're going to be drawing more carbons than anything else. So you should always, always, always have an octet of electrons around oxygen and nitrogen in the structures that you draw. If you draw a structure and that's not the case, you've drawn a wrong structure. Carbon, on the other hand, sometimes will be short. So sometimes carbon lacks an octet, but that's okay. We're going to be seeing actually lots of structures where carbon lacks an octet. Those structures are called carbocations. So a carbon with a positive charge and 6 electrons around it is a very, very common pattern, and that's okay to draw. Now, if you're considering or you're consulting other sources, one of the rules that people have for checking resonance structures and assessing resonance structures is phrased in a different way, but it's really getting to the octet rule. It tells you to maximize the number of bonds. Try to put as many electrons as possible into bonds. So you may see that, I'm going to put that in quotation marks, put as many electrons as you can into bonds. Or could be said something like maximize covalent bonds, the number of covalent bonds. That's saying the same thing as, is the octet rule satisfied? The more electrons you have in bonds, the more likely the octet rule is to be satisfied for all the atoms. So if you run across that way of saying it in from some other source, that's what it means. It means the same thing as checking the octet rule. Okay, so let's look at a couple of other things, or a few other things. The next thing you'd want to check, or another thing you'd want to check, so really it's the octet rule is the very first thing, and then the other things, these other 3 factors that we're going to look at, that's going to depend on the structures that you have. Okay, so some of them you might not even need to check, and others you will. So you're also going to want to minimize both the number and the magnitude of non-zero formal charges. So a non-zero formal charge is just a formal charge that's not zero. Okay? So minimizing the number of formal charges. That means you want as few non-zero formal charges as possible. So that's one thing. But you also want to minimize the magnitude. That means you want the charges themselves to be as small as possible. What that means is that plus or minus 1 is better than plus or minus 2. Okay, so you want these numbers to be small. Now, in practice, for the structures that you guys are going to be drawing in this class and in the next semester, your formal charges, I can't even think of a case where you're going to have a formal charge that's not plus or minus 1. So if you're drawing structures and finding charges of plus or minus 2 or greater than that, there's probably better structures that you can draw. So you want these charges to be as small as possible. Okay, another thing that you can assess, let's say that you have a negative charge in the molecule. Maybe you're dealing with an anion. So it's an anion because it has a negative charge associated with it, which means that at least one of the elements in there in the structure will have a negative charge on it. So in such cases, the best structures are going to be the ones that put that negative charge on the most electronegative elements. Let's look at an example of something called an enolate ion. So here's an enolate ion. The carbon on the right has a lone pair. It has two hydrogens, which I have not drawn in, and as such, it's going to have a negative formal charge. We can draw a resonance structure. Actually, let's fill that in a little bit more. Okay, there we go. Okay, so we can draw a resonance structure for this involving one of the resonance patterns that we're going to look at shortly. And we would start an arrow at the lone pair on the carbon and point to a bond, point to this bond rather, not just any bond, but point to the bond that joins that carbon to the carbonyl carbon. So what this arrow is saying is we're taking that pair of electrons and we're putting it into a bond. If we just stopped there, the carbon in the middle of the structure, the carbonyl carbon, would have too many electrons around it. It would have 10. So a pair of electrons has to move away. So we're going to take a pair out of the double bond and push them up onto the oxygen. So remember that the arrows start where you have electrons, and they point to where those electrons end up in the next structure that you draw. So our first arrow, those electrons ended up making a double bond, and the second arrow, those electrons ended up becoming a lone pair on the oxygen. Now that the oxygen has 3 lone pairs and 1 bond, it has a negative formal charge. Now that the formal charge, the negative charge, is on the more electronegative element, so oxygen rather than carbon, that makes this the major contributor. So when possible, you want to get the negative charge on the most electronegative elements you can. Now, as a side note, since we're talking about charges, people get a little bit worried about positive charge. So let's make a note about that. The positive charge, this is where people get messed up. Positive charge is okay on an oxygen or a nitrogen. So these are really highly electronegative elements. And so for various reasons, people feel uncomfortable putting positive charge on them. It's okay to put a positive charge on an O or an N as long as the oxygen or the nitrogen has an octet. So an example of something like that, very common example, might be something like this guy. So that oxygen has a positive formal charge. I'll leave it to you to prove that to yourself using the formal charge formula. And it has an octet of electrons. So this is a perfectly valid and reasonable structure. Okay, so the final point that I'd like to go over with you involves something called minimizing separation of charge. Okay, now when we're talking about separation of charge, we're talking about the separation of positive and negative charges. When positive and negative charges are separated from each other in space, that's a higher energy situation than if they're brought closer together. So their Coulombic attraction, as you bring the charges closer together, minimizes the energy of that system of charge. So let's see what we mean by minimizing separation of charge. So let's draw a structure. Like so. Now I'm going to put some numbers on carbons so that we have some points of reference to talk about. And then I'm going to draw some resonance for this. Now, first of all, what kind of functional group is contained here? This is a ketone. And the ketone part of this is conjugated with the carbon-carbon double bond. So it's conjugated with an alkene. So remember that one of the ways that you can recognize a conjugated pattern is a double, single, double bond pattern, which is what we have going on here. So this is both a ketone and it's a conjugated system. Okay, so the resonance that we're going to invoke is going to be the following. We're going to start an arrow at the carbon-carbon double bond between carbon 3 and carbon 4. So start an arrow there and push a pair of electrons over to between carbon 2 and carbon 3, which necessitates moving a pair of electrons away from carbon 2. So we're going to pull a pair out of the double bond between the carbon and the oxygen and put them on the oxygen. Notice how all the atoms stay in the same places. Let's maintain our numbering. And let's assess. Okay, so our arrows told us some things. For example, the first arrow that we drew that moved electrons away from the 3-4 bond and into a 2-3 bond, what that does is it leaves carbon 4 with a positive charge. Again, use the formal charge formula to prove that to yourself. The oxygen started with 2 lone pairs, but then we pulled a pair out of the carbonyl pi bond or double bond and put those on the oxygen as well. That gives the oxygen a negative charge. What we have now is what's called separation of charge, because the positive and the negative charges are separated from each other in space. The farther apart they are from each other, the worse it is. So a separation of charge means that the positive and negative charges are separated from each other by space. The larger the separation, the less important the contributor. Let's compare this structure that we just drew to another one that we could have drawn. So in the original structure on the left, we have a ketone. Now we could have done what we did in formaldehyde. So leaving everything else alone, we could have simply moved a pair of electrons out of the carbonyl double bond onto the oxygen, and that would give us this structure here. This structure also has a separation of charge, but it's a smaller separation of charge than the one in the structure directly above it and to the right. So this has a small separation of charge, or let's say a smaller separation of charge. Let's actually label these structures. We'll call the original one A. Let's call this guy B. Let's call this structure over here C. Okay, so this structure B has a smaller separation of charge because the charges are closer together. Than they are in structure C. Okay, so one final point about this. Remember that we talked about, up above, the fact that the minor resonance contributors can tell us something about the molecule. Look at structure C. In structure C, there's a positive charge on carbon 4. What that could suggest is that, again, something that has extra electron density that it might want to share could be attracted through a Coulombic attraction to that carbon. Now, we wouldn't have known that unless we had drawn this resonance contributor, because if you look at structure A, carbon-4 is not bonded to something that's more electronegative than it. Okay, so it's not that easy to see that it has a partial positive charge associated with it by virtue of the fact that there's an oxygen, doesn't happen to be next door, but it's close enough that it can be pulling electron density towards itself. So this is an example of a case where a minor contributor can give us a little bit of inside information as to how something might react.